Welcome to our final week of class. You can think of this week as a little bit of a victory lap for having survived the semester. You should be really proud of the progress that you've made. This is not easy material to get through online, let alone in 8 weeks. So to wrap things up, I want to talk a little bit about how to choose which statistical test to use, and then give you a little bit of an overview to multivariate statistics, which are a branch of statistics that you might be coming across in some of the journal articles that you read, and also maybe in some of your dissertation topics. So taking us back to the beginning of the course a little bit, we talked a lot about the difference between independent, dependent variables. We talked about different ways of measuring our variables, the issue of sample versus population, and the idea of between versus within subjects research design. So all of these factors are actually driving the type of tests that we're able to run. And it may be that when we're designing our research, we're thinking about this from the get-go, or it may be we already have data, or perhaps we're using archival data, and then we really have to know which is the appropriate test to use, what are we able to do with our data, what kind of research questions can we answer. And again, there's more than one way to answer any research question. If you recall on one of the homework assignments, I talked about a researcher being interested in the relationship between years of education and income, and there's a lot of ways you could answer that question. If you leave those variables as if you leave those variables as continuous or interval ratio data, you can use a correlation coefficient or regression equation. However, if you begin to categorize some of those, say you categorize education by degree type and use that to predict income, which is again measured at interval ratio, in that case we might use ANOVA. So we're answering the same type of question, but depending on how our data, how our variables are measured, will really drive the type of statistical analysis that we can conduct. This graphic here is an example. If you are interested, you can Google this. It's a statistics tree or a decision-making tree for statistics. And basically this breaks down different types of statistical tests and the different questions you might ask yourself when trying to figure out a test. You can Google this. There are way more complicated versions of it. I like this one because it's nice and clean and hits a lot of what we covered in this course. But again, it's definitely not the whole story. There's much, much more. So feel free to browse around if you're interested in learning more. But you can see at the top here, on the far left, this is where we started out. We started out with talking about only interval variables. So again, if we were talking about an association, we talked about a Pearson correlation coefficient. When we were talking about prediction, we talked about simple or multiple regression. This third branch over here, only nominal variables, was our most recent unit when we talked about chi-square. And again, we had the chi-square goodness of fit test when we have one nominal or categorical variable, and the chi-square test for independence when we had more than one. The second branch here to come back is when we have a combination of a nominal or categorical independent variable, and again, an interval ratio or continuous dependent. So again, something we want to take the mean of. So we can talk about our factorial ANOVA fits in here, where we have either between groups or within, or a combination. Down here we have our within groups one-way ANOVA, which we also called repeated measures, our one-way between groups ANOVA. Way down at the bottom we have our t-tests, our paired samples and independent samples. And then on the far left we have z-tests and single sample t-tests. We didn't cover those in this course, but they're very simple and are actually not very commonly used. So we didn't really go over those. And then finally, this fourth branch deals with ordinal variables. So these were mentioned in the text. I didn't really spend a whole lot of time going through SPSS and how to run them because, again, they're not really common in the literature. You might see these once in a while when people have rank order data. But in general, those first three branches, branches 1 through 3, are the ones that you're going to see quite a bit when you're reading research. So this gives a nice breakdown on, first we want to talk about what our independent dependent variables are. We want to think about how they're measured, and we want to think about the research design, whether it's a within or between groups or a combination of the two. So like I said before, there are far more statistical tests here. These are just kind of some main categories that you see when we talk about univariate statistics. So the common theme in all of these is we've talked about having a single dependent variable. And in all of our examples here, our dependent variable has been either something continuous or interval ratio, like in branch 1 and 2, or it's been a frequency, like in branch 3, or it could be a rank order, like in branch 4. But a lot of times when we're doing research, we're interested in more than one dependent variable. So that's where our multivariate statistics come into play. You can imagine a lot of times in research that we're interested in multiple outcomes. So in healthcare, for example, we might not be just interested in someone's weight. We might be interested in their weight, their cholesterol, their blood pressure, their glucose levels. We're interested in all of these indicators of someone's overall health and well-being. Same thing in education, we might be interested in students' achievement, but we're probably also interested in their attitudes, their confidence, how much they like a particular subject. And of course, we're interested in multiple subjects at the same time. So how do we design studies that can assess multiple outcomes that we might be interested in? So multivariate statistics basically is talking about techniques for examining relationships among multiple variables at the same time. So again, we're talking about more than one dependent variable or outcome variable, and we're also talking about more than one independent variable. So this type of analysis, again, is desirable because a lot of times we think that our dependent variable or our outcome of interest is affected or influenced by multiple things. And this is where we're getting into kind of that big data phenomenon that we're seeing. If you talk about websites like Amazon, it's crunching all of the data that you've ever put into that website and data from other people, and it's generating these multiple predictions, in this case of consumer behavior. So there are a number of multivariate statistical techniques. There are entire books on this. You can take an entire class. And I just wanted to hit a couple of the highlights that I think are most common in journal articles in your field, and also ones that I've seen students sometimes do for their dissertations. So I want to talk a little bit about path analysis or structural equation modeling, multiple analysis of variance or MANOVA, and then logistic regression. So again, this is just scratching the surface, and I just want to give you a conceptual overview of each of these and a little bit of an example. Again, if you Google statistics tree or branches of statistics, you can see there are far, far more of these. I think even if you just go to Wikipedia, there's a list of at least 25 different tests. So we're just going to cover these top 3. The first one that I chose is path analysis because you see this in journal articles pretty frequently, and it's become an increasingly popular technique probably in the last maybe 15-20 years or so as we've developed different computer software programs. So path analysis is a graphical form of multivariate statistics. So we have these graphs that are also known as path diagrams, and basically these are depicting correlations among variables as well as the directions and the paths along which these relationships travel. So let's look at an example. This is something that you might see in a journal article. As you can see, we're interested in a couple of variables here. We have this idea of achievement in the very center. We think that achievement is related to some other issues, such as your math ability, your attitude towards chemistry, and your prior knowledge that you have on these topics. So instead of simply running a series of correlations or a series of regression analyses, a path analysis allows us to simultaneously test all these relationships at the same time. So we talked before, when we talked about the difference between t-tests and ANOVA, we talked about this idea that the more tests we run, the more our type 1 error rate is compounded. So each test that we run has that 5% chance of making an error, and the more tests that we run, the more that this error ratio is magnified. So a path analysis allows us, just like ANOVA, we're testing for simultaneously relationships at the same time. So you can see here the numbers on the paths. We have arrows that are indicating the relationships, what goes with what. We have an R squared, and again, that's just the amount of variance explained in the middle there of achievement. And you can see these numbers are actually corresponding, these are beta weights. So if you think back to multiple regression, we had beta weights for each of our predictor variables, and that's what these are in a path analysis. So you'll see this in journal articles quite frequently. In order to run a path analysis, it's very difficult to do in SPSS on its own. There is kind of some back-end computations you can do, but generally you'll want some kind of add-on program. So there's a couple of programs where you can actually draw out these boxes and arrows and use that to run your statistical analyses. So it's kind of beyond the scope of this class, but just wanted you to have a general awareness on what this is and basically what this model is telling us and what these different coefficients mean. So again, it's very similar to multiple regression. It's calculated in a very similar way on the back end of this. And our ultimate idea is we're trying to predict the amount of variance explained in a specific outcome. Our second type of multivariate analysis is multivariate analysis of variance, or MANOVA. And our MANOVA extends our ANOVA technique to studies that have two or more related dependent variables while simultaneously controlling for the correlations among them. So for example, let's say that we want to do a health study. We have three groups of teenagers. We have a group that exercise regularly, those who exercise every once in a while, and those who never exercise. So in our traditional ANOVA, we would call this a between groups because the teenagers are in separate groups. You can't exercise regularly and simultaneously never exercise. Believe me, we've tried it all. So in a traditional ANOVA, you would have those three categories as your IV, and you would want to choose a dependent variable, something that you can take the mean or average of. But a multivariate analysis of variance would allow us to have multiple outcomes and multiple dependent measures. So things like weight, heart rate, and respiratory rates. We could test all of those simultaneously. To actually run a MANOVA in SPSS isn't too bad. I want to walk through just a quick example here. Again, you don't need to do a homework or anything on this. I just wanted to show you as kind of a conceptual understanding to get an idea of what all SPSS can do. So we'll flip over to SPSS and we'll look at kind of a fun example on how we can use our multivariate analysis of variance. So we have SPSS open here, and this data set I think is kind of fun. This is actually a data set that has information about hot dogs in it, because who doesn't love hot dogs? Nice weather is starting up, so it seems to be the season for them. So you can see here I have different types of hot dogs. If you scroll down, we have beef, we have meat, which is a very ambiguous term, which is a combination of various things, beef, pork, etc. And then at the bottom we have poultry. So we have three different types of hot dogs. If we go to variable view, I've coded these 1 through 3, so you can see the corresponding labels there. You can see I've defined those as nominal variables, and then we also have calories and sodium, which are both measured as interval ratio or scale variables in SPSS. So we could do two tests here. We could do a traditional analysis of variance. We could do an ANOVA looking at calorie content. Does that differ significantly by hot dog type? We could do the same thing but sub out sodium, or we could do a multivariate analysis and we could test both of those at the same time. So the research question would be, do both calories and sodium differ significantly in terms of different types of hot dog? So to actually run the MANOVA, it's under our Analyze menu. When we did our regular univariate ANOVA, we used this tab General Linear Model, and if you recall, we used univariate and we also looked at repeated measures. So the last one is right in the middle there, multivariate. And in this case, it looks very similar to our regular ANOVA, except now we can enter more than one dependent variable. So I'm going to transport both calories and sodium into the dependent box, and then hot dog type is going to go as our fixed factor. And again, you could get more complicated. You could add multiple independent variables. You could add a covariate, but we'll keep this example very simple. Over on the side here, we have some different options, and under post hoc, I'm going to click that because again, we have three different categories. So we're going to want to know which hot dogs differ significantly from each other. So I'm going to take hot dog type factor and just transport it over and tell SPSS that I would like a Tukey post hoc for that. And I'll go ahead and click OK. And then we always like to get some descriptive statistics. So under options, we can display means for different types of hot dogs. So I'll go ahead and click that and then hit continue and OK. So you can see that ran incredibly quickly. We have this first box of output that just tells us how we labeled our hot dogs, how many were in each category. We have our descriptive statistics for both calories and for sodium. You can see kind of the breakdown of it there. If we scroll down to this third box of output, you can see it's called multivariate tests. And this is kind of analogous to our regular ANOVA when we were testing for that overall F-test. So again, our F-test told us that there were significant differences between our groups somewhere in our data, but it didn't tell us specifically where. Same thing with our multiple regression. We had that overall F-test that said that we had a significant predictive model, but it didn't tell us which predictors were significant. So here you can see that we have a significant F-test. And again, there are a couple different statistics that you see reported. I think the Wilks lambda is the one that you see most frequently. And again, these are just different variations of the same test, but if you look at the F value column, you can see that the take-home conclusion is the same. Our F value has not changed, our significance level has not changed. So oftentimes these different variations of the test don't actually make a difference, but always kind of check with your advisor or the field that you're in or the type of journal that you're interested in submitting to kind of see what the convention is. So here this is telling us that our F statistic, it's over 1,000. Our significance level is very small. So it's telling us that we have significant differences in our hot dogs somewhere, and it's either having to do with sodium or it's having to do with calories. So how do we drill down further? We can scroll down a little bit more here, and you can see here we have a slightly more complicated tested between subjects effects. So we can look first, we have our overall corrected model. And you can see we have a row for calories and a row for sodium. And if we go across, we have an F statistic for each of these. So you can see here that we have a significant F value associated with calories. Our sodium F value is not reaching significance. So what this is telling us is that we have significant differences in calorie content, but we don't have significant difference in sodium. So again, if you just looked at the previous chart, the multivariate table, it's telling you you have significant differences somewhere in something, but it's not being very specific. So the tested between subjects effects is giving us a little bit more information. But again, we would want to know which hot dogs differ significantly in calories. So we have to drill down a little bit further. So if we go down here, we have our marginal means. So again, this is just breaking them down by category. So when we're looking at this calorie part, we see that beef hot dogs have an average calorie count of 156. The mystery meat ones are at 158, and the poultry ones are at 118. So again, the question is, are these means significantly different from one another? And we'll have to look at our post hoc Tukey test in order to determine that. So here we have our multiple comparisons table. It looks just like your regular standard ANOVA, except it's a little bit more involved because we have them for both dependent variables. So you can see here, if we check out our significance column, we're finding a significant calorie difference between beef and poultry and also meat and poultry. So our take-home message would be, if you're going to eat hot dogs, well, the sodium will probably kill you either way. They're high for all of them. But if you're concerned about calories, the poultry hot dogs might be a better alternative to the beef or the mystery meat ones. So you can see here we could have come to a similar conclusion by running two separate univariate ANOVAs, but we were able to kind of kill two birds with one stone, if you will, and we were able to test both of those dependent variables at the same time while controlling for potential correlation between the two. Going back to our slides, again, that was our brief synopsis of MANOVA and SPSS. Again, it's pretty simple to run. It's not too different from the traditional ANOVA that we practiced in class. It's a little bit more involved. There's some more boxes on the output, and it takes a little bit more thinking to kind of interpret that. But it's definitely something that if you're interested in for your dissertation, you could definitely run this using SPSS. So again, we just had the sample output there if you want to play around with it on your own. And last but not least, we have our final test. I picked this one because I do see this especially with some of the nursing students and actually education as well. You'll see this pretty common in journal articles, but we have logistic regression. So we have a picture here. You can see this red line, it's labeled linear probability model, and you can see this was just our regular regression line. So that was our y equals mx plus b, our y equals a plus bx, whatever the formula was. So this is our standard equation of a line, and we talked about using that line to make predictions with multiple independent variables. So that's when we have a interval ratio or a continuous dependent. So again, something we can take the mean of. But a lot of times in some areas, the dependent variable that we're interested in, it might be categorical. So if we think about education, you might think of either passing or failing a class. You might think of successfully completing college or not. So some things are just black and white, yes, no. So how do we develop a model that can test that? Same thing with healthcare. Either someone develops a specific disease or they do not. Either they suffer from this condition or they don't. So if we were to graph that, it might look something like this purple curve, or this is a logarithmic function. If you think way back to high school algebra when you learned about different functions, we talked about parabolas and logs and natural logs. So that's what this is getting at. So you can see on our y-axis, we have two options. We have y equals 0, y equals 1. So we can think of those as yes, no. So we're going to use multiple independent variables, or one or more, in order to predict a categorical variable, a yes-no response. So you can see that we can't use our standard straight line anymore. We have to use kind of this purple S curve, or we use a logistic model. So in logistic regression, the dependent variable that we want to predict is dichotomous, which is sometimes referred to as binary logistic regression. So what we're doing in this case is we're estimating the probability of an event occurring because there are only two possible outcomes. So that's our dependent variable. Now our independent variable can be categorical or it can be continuous. And again, the relationship between our IV and our DV does not have to follow that classic straight line like in regular regression. So, for example, in healthcare, low levels of blood pressure might not matter in some instance, but high levels do. So that might be a variable that we categorize into high or low. And what logistic regression is going to do is it's going to compare the best model against the most frequent category. So we want to know whether or not we can improve our predictions. So at the very bottom here, before we had our regression line, again, that y equals mx plus b. And this box down here has our logistic regression equation. So we have our prediction is equal to 1, and on the denominator we have 1 plus, the E stands for natural log, and up there we have an exponent. We have a plus bx with a negative sign over it. So you would never do this by hand, but just conceptually know that this is a logistic regression equation. It's the same idea as our simple regression equation. It just looks a little bit different because we're accounting for that different shape, that logistic curve instead of a straight regression line. But actually, this isn't too bad to run in SPSS, and we'll actually be using SPSS to pull these coefficients A and B, just like we did for our multiple regression. So we have some kind of historic data here. We're talking about the launch of the Challenger, which was several years ago. But as we know, this was a pretty serious tragedy that happened. The Space Shuttle Challenger launched, and then shortly after it went up in the air, it exploded. Really big deal. It was one of kind of those first disasters that was televised, and just really strong emotional reaction to it. So you can see here one of the problems that was suggested, kind of the main blame was this idea of destruction on the O-rings. So O-rings are these little rubber rings that go around the rocket engine parts and help keep the rocket together, helps keep air pressure normalized, all of that good stuff. So later, when they examined the cause of the Challenger disaster, they found that there is deterioration on these O-rings, that they're damaged. So our question is going to be, does temperature predict the likelihood of thermal distress on O-rings? So if we go back one here, we have some data, and we know that the day that the Challenger launched, it was unseasonably cold. So the idea is that we think that temperature might cause deterioration among these O-rings. So can we predict, using logistic regression, the likelihood of a disaster event, basically? So we want to know, what is the probability of thermal distress when the temperature is equal to 31 degrees? That happened to be the temperature that day, which again, we're talking about Florida. That is unseasonably cold and very unusual. So we'll jump back to SPSS and we'll look at this. Again, we're going to use the Analyze menu, the Regression menu just like before, but we're going to click instead on Binary Logistic Regression. And we'll enter our IVs and DVs just like before, and then we'll look at what some of the output looks like. Going back to SPSS, we have a new data set here. We have data from 23 different flights from NASA. We have the temperature of the day that was launch day. And then this third column, we have thermodistress, which means damage to the O-rings. So you can see that it's been coded with yeses and nos. If we go to our variable view, it's a nominal measure, and you can see I've categorized it with 0 equals no, 1 equals yes. So the idea is, can we use pre-existing data from NASA, can we use historic flight data to generate a prediction equation, just like we did for multiple regression, but in that weird S-curve model in this case? Can we generate a prediction equation and then plug in what happens when the temperature is 31 degrees? You can see here when we're looking at the temperature, it looks like we have about a high of 81, and it looks like the low, scanning down the column, we got a 53 and a 58, but nothing even close to 31. But the idea is that we can use this historic pre-existing data to generate predictions about the future and future flights. To run our logistic regression, we'll go and use the Analyze menu. We'll drop down to Regression. And we're going to select this one, the binary logistic. So again, that's because we have a dependent variable that is categorical and it has two conditions. So either yes or no, pass, fail, graduate or not. If you wanted to have a dependent variable with more than two levels, you'd use this next one down, the multinomial logistic regression, but that's even more beyond the scope of what we're going to do here. So we'll click on binary logistic. And you can see our input box doesn't look too terrible. We're going to put our dependent variable, which was thermal distress, going to transport that over. And then I'm going to take our independent variable of temperature, and I'm going to transport it into this box that's labeled covariates. I'm not going to do anything with the flight variable. Again, that was just kind of a label so we know which flight is which. We won't do any additional options or anything on the side here. We'll just keep this example really simple. So we have our dependent variable, we have our independent, which goes in that covariate box, and I'll go ahead and click OK. All right, so you can see here that we have a couple different blocks of output. I don't want to get too bogged down in the interpretation of the logistic regression. I do just want to say that this first one, we have block 0 as the beginning block. This is kind of like our starting point, so it's really not testing our prediction. This is rather just an illustration of how the data currently look. So you can see how we've classified things. We have the yes or no with the thermal distress. What we really want to do is scroll all the way down to the bottom. So here we have block 1, method equals enter. And what it's doing is it's testing our overall prediction model, and in this case it's using a chi-square test. So you can see, just looking at our overall chi-square model, it's giving us a significant chi-square value. And then if we scroll down a little bit further, at the very end we have this table labeled variables in the equation. And this might look kind of familiar because it's analogous to our multiple regression. You can see here we have a B coefficient that's associated with temperature, negative 0.232, and then we also have a constant. So just like our y equals mx plus b, we're going to pull our coefficients from this column right here. So we're going to take the b values for temperature and also the constant or the intercept. You can think of it that way. So if we go back to our slideshow, here we have the variables in the equation box that we just saw in our SPSS output. And here I've broken down that equation from before, again, that logistic model equation. And all I did was plug in the intercept here for A, the coefficient associated with temperature for B, that negative 0.232. For X, I've plugged in 31 degrees because that's the temperature that we're interested in predicting for. And you can see you'll need a slightly fancier calculator to do this because you have to be able to do natural logs. But if you calculate this, you can see we get this final answer of 0.9996. And what this is telling us is that the probability of a thermal distress event when the temperature is at 31 degrees is 99.9%, excuse me, 99.96%. And our SPSS model told us that that was statistically significant. So we would be pretty confident in saying that when the temperature reaches that degree, we're very certain that there's going to be some kind of ill effect, some kind of thermal distress event. So that's just a little example of how logistic regression works. Again, you might see this in healthcare and education. I've known a couple students that have written it up for their dissertation if they're looking at pass-fail rates, for example, with some of the standardized nursing tests. So I just wanted to give you a little bit of an overview about it. So hopefully that's helpful. Again, we talked about path analysis or structural equation modeling. We talked about MANOVA, and then we talked a little bit about binary logistic regression.